Welcome all to this new webinar from MyRisk in association with the University of Liège. In today's webinar, we will have Charles Troupard from the University of Liège talking about DIVA-ND, which is a software tool for data interpolating variational analysis in n dimensions. So as we've been doing in previous webinars, this is an informative webinar and it's going to be recorded for dissemination purposes for the remaining parts of the community. But we are going to be talking here, if you go to the right-hand side, about these four first aspects in this webinar. What is DIVA-ND or DIVA-ND? What it can do for you, how the tool is implemented, and how to install it and develop your own applications. After that, we will stop the record and we will go for some questions. We will stop the record so that you're not feeling shy to ask whatever you want to ask. And also because this webinar is going to be followed by an upcoming on-site 3-day training at the University of Liège in Belgium, next year in late January from the 20th to the 22nd of January. So if you want to, after this webinar, attend the session as well, you will find the registration link in our website. And if you are already registered and you want to know more about practicalities, you can also ask us in the question and answer sessions. But this is what I wanted to show you from my side. I don't want to steal more time, and I'm going to give the floor to Charles Troupard. Charles, whenever you are, the floor is yours.
Okay, let's see if this works.
It works. We can see it.
Okay, so welcome everybody and thank you for attending this webinar about DIVA-ND. So DIVA-ND is a software tool and it means data interpolating variational analysis in n dimension. As Benyat has already said, it's important to understand what we are doing and if it can be interesting for you, for your data, and for your research. I like to start always with the clean slide showing what we do, because sometimes people say what does it mean, gridding, interpolating, etc. So in this case, we have a figure on the left side. It's temperature observations in the sea, and what we want to obtain is the continuous field. We call it a gridded field, which is represented on the right. How do we do that? There are many techniques relying on different mathematical background, etc. But the idea is this: you go from in situ sparse data. In this case, it's oceanography, but it can be any type of geo-reference data. And you want to get a regular, continuous gridded field on a regular grid. The technique that we use is DIVA-ND, and I will show you how it works, why we think it's relevant for the project, for you to learn, etc. So I have an alternative title for my presentation because, okay, it's about DIVA-ND, but I will say 4 good reasons why you would not like to use it, because sometimes people say, I don't want to use it, and there are good reasons. So that would be the alternative reason to not use it. So for example, the first one is that the algorithm is very complex. And I told Benyat just before the talk, it's very, a lot of mathematical equations, etc. It's complex, so maybe you don't have time to learn, and I think it's a good reason, but at the same time, you are here and my colleagues to help you. Another reason not to use it is that you already have your interpolation tool. It makes sense, so of course we cannot reinvent the wheel, but we think we have developed a very good tool, open source, etc., that can be useful to everybody. So the reason you might say, okay, it's only for oceanographic data. You don't care about the oceanographic data. You want to apply something else. And in fact, it works because it's based on mathematics, and the data themselves, the code doesn't need to know what types of data. As far as you have coordinates, it can be longitude, latitude, time, anything. If you have coordinates and measurements, we can apply DIVA-ND. The fourth reason why people sometimes they say, no, look, Charles, I cannot work with Diva, is that the code is written in Julia. And you might say, yeah, Julia just a programming language. that we won't hear about in a couple of years. So that's pretty good reason not to use DIVA, but we'll dig a little bit deeper into the reason and try to show that, yeah, it makes sense to use it. So that's the scheme of the presentation. To of the center DIVA-ND, we'll talk about the algorithm, we'll talk about the GLA language and some applications of DIVA-ND. So first, let's start with the algorithm. And as I promised, I won't show too many equations. So why is gridding in the ocean complex? So gridding in general is complex because we have to deal with a huge amount of data points. In the case of oceanography, it's typically millions or tens of millions of observations. It means that some software, some codes are not able to deal with such huge amount of observation and cannot perform the gridding, cannot perform the interpolation. In oceanography, we have also the presence of obstacles. By obstacle, we mean coastline, the bottom, etc. It means if you have information, for example, in the Mediterranean Sea, you don't want the interpolation algorithm to propagate the information across the land. So it means the land acts as a barrier to, and prevent the information to be transferred from one region to another. So it's highly anisotropic, and this has to be taken into account. Also, we have heterogeneity, both spatial and temporal. What do I mean by that? For example, this is the number of observation of silicate around the time. So on x-axis, you have the year, and the y-axis, you have the number of observations. What we can see, it's typical for the ocean, but probably for other sciences, that you get a lot of data in some periods, but other periods you get much less data. So this you need to take that into account when you interpolate. It's the same with the months. It's typical in oceanography that you go at sea, you don't go in January and February, maybe because the sea condition not good, but you would go more often in spring, in summer. That's why the distribution is like that. So how do we perform the gridding? As I said, DIVA-ND, it's the interpolation n dimension. We have the code available on GitHub. So it's a code written on Julia. We'll talk about that later. The code is open source, meaning that everybody can download it, reuse it, modify it, and of course submit issues. And the paper was published already like 11 years ago in the GMD, Geophysical Model Development Journal. So we have the link there. Once the presentation will be shared with you, you can get access to these also, to the URLs. So how does it work? You imagine here we have observations. These black dots are observations in one dimension. So we can assume that the x-axis is the time. And how does DIVA works is that if you perform a strict interpolation, which is the red line, it means that the interpolation has to contain all the observation, which is why you have the red line. But with DIVA, what we want to do, we want to be close to the observation, and the closeness to the observation, that's what I've represented by the springs here. So the spring, you have to imagine that it pulls the interpolated field. So in this case, the black line is pulled toward the observation. Why do we do that? Because we cannot trust 100% the observation. We have different types of errors. Errors due to the instrument, errors due to the synopticity, many types of errors. It means you trust the data, but the field that you want to reconstruct, the gridded field that we've seen at the beginning, should not be too close to the data. That's the main principle of DIVA. So if we want to talk about an equation, so how does it work? Mathematically, we want to minimize a cost function that we call J. So J and the variable phi is the function that we want to estimate. It is the gridded field. We have basically two terms. The first one measure the closeness to the observation. So we assume dy is the observation at a given location, and phi is the value of the field at that observations. Then the second term will measure the regularity, or so it can be also called the smoothness of the solution. Because if we represent salinity or temperature field, we know that it has to be relatively smooth, regular, and without any too strong gradients. This is measured by the second term here. So the basic of DIVA is to minimize this function, functional j, and will give you the best value for the field, which is the gridded field. It's really a simplified version of what we are doing, but basically you need to remember more this picture with the close to the data, but not too close, and to be smooth. Why do we use DIVA-ND? Because I've said before, we can deal with millions of data points. It's not the case of every technique. You can take into account obstacles. In our case, for oceanography, it's the bathymetry, the coastline, but in other domains could be different. We generate a gridded field, but also an associated error field, showing where you can trust the interpolation, where you have data, basically. It's fast. We need to be fast because this kind of interpolation has to be repeated many times. And also the open source code is something that makes people want to use it because it's not a black box. You can really see what we're doing. How would the typical workflow works? First of all, the most important, you need to read the observations. We used to work a lot with NetCDF file, but reading data really depends. It's domain specific. Sometimes people have different format, but it's not a problem for us because you can adapt the reading tools that we have, and we always find a solution to read the data. The idea is that we get the value measured and also the coordinates. Then the user will need to specify the domain. By domain, I mean, for example, I want to work on the Mediterranean Sea. Need to set the grid resolution, for example, 1/4 of a degree, and the time period over which I want to interpolate. Third step is to create the land sea mask. What does it mean? Land sea mask, it means we want to be sure that the interpolation is only performed in the sea, because seawater temperature doesn't have any meaning on land. So we will create what we call a mask, which will take a value of 1 when you are on land, 0 on land, and 1 on sea. If we work on the land, of course, it would be the opposite, but the idea is that we create a mask where we specify the region where the interpolation is performed. We have to optimize a few analysis parameters. Number 5, set the metadata. It's quite an important step because we want to be sure that when you create products with DIVA-NDs, that the data providers are correctly acknowledged. So in the metadata and the metadata of the result that we create, we always keep trace of where the data come from, and all the types of metadata are relevant. But it's really something that in the past, we maybe were not sufficiently correct with that, but I think it's metadata is really a crucial aspect. And then we produce the gridded fields. So now from that, I would say a few good reasons to use DIVA-ND. It's fast, open source code, we've already said that. We can deal with any type of geo-referenced observations and the capacity to deal with millions of data points. So now let's talk a little bit about Julia language. Maybe some of you know. I know it's not the most used language. In fact, in my case, from my experience, I was working with Fortran in the past, and then to switch to MATLAB. Then from MATLAB to Python, because the institute where I was working didn't have any license for MATLAB, so I went to Python. And now, like I would say 6-7 years ago, I had to learn the Julia language because it was the language that we coded the DIVA-ND at my institute. So I would say starting from using Julia some years ago was not easy. The documentation was not so easy, installation was not so nice. But 2 or 3, let's say 3 or 4 years ago, it really changed, and now it's very easy to install any type of machine. It runs on supercomputer, etc. So everything for students, for us, it's a really good investment in time to learn Julia. So what is Julia? You have the main page here. So Julia is a programming language. It has 3 main characteristics, or even more, but we say fast. So it performs very well, and you can even use the GPU computing, parallelism, etc. So it's something really needed with DIVA-ND. It's dynamic, so it means that the variable type is determined when you run the code, and also it's reproducible. So if you're a European project, you hear a lot about reproducible, and I think it's one of the main advantages of Julia, because we work with environments, It is of environments that are stored in a file. You can share these files with your colleagues, with other users to see exactly which combination of packages, etc., that you've used. So why did we use Julia and not R and Python? I put this question here because it's a question that we've heard a lot in the past. So R, I've put on the right side here the TIOB index. It's a way of measuring, assessing the popularity or usage of a language. So as of November 2025, R has an index of 1.7%, which is not a lot, but still it's in the top 20 languages. It's R has a very large user community. If you know biologists, statistics, etc., many people are using it. In fact, it's specialized in statistic analysis because you have lots of modules available and a lot of high-level packages. And on our side, we would say the performance is rather poor when you have to compute with huge data sets, many millions data points, very fine grid. It doesn't work very well, at least in our case. And so we think there's a lack of a package with a high dimensional variational constraint, which is what we've implemented in DIVA-ND. So R is very good, very popular, but in our case, it did not work. Then we have this Python. At the beginning, I thought, okay, if we write the code from scratch, we should go to Python because, again, it has a wider user community. And you can see in the index, we're at 23%, which is the most popular language, I think, in 2025. It's a language that is multi-purpose, but again, the problem for us was the speed. If you want to achieve high speed with Python, you need to use PyTorch or Numba or different types of modules that sometimes have that complexity of the code and some overhead. So we checked with different tests and we were really faster with Julia. So Julia, of course, it has issue. The first issue is that a smaller user community. It's what we would call a young language because it was started in 2012, and yet the user community is growing fast. We have always lots of more users, which is always good. Language is incredibly fast. We can test against code compiled with Fortran and C++, and Julia is very good at that. If you read documentation about Julia, they always said, okay, bridge the gap between scripting and compiled language. What does it mean? That Julia, in fact, is a compiled language, but you don't see the compilation. You write your code, and when you execute it, it's compiled in the background. You don't see it. So it's what they call the JIT, just-in-time compilation. And it's much easier than Fortran. We have to put the compilation option, etc. So it's something that you don't see it when you code, but in fact, the code is compiled. Also, very important for us is that the syntax of Julia is math friendly. You have a lot of maths, so we need to be able to transpose these equations into a code. Some publication about Julia, sorry. So maybe the most important one was in 2017. So Julia, a fresh approach to numerical computing. So they really explain how they started Julia, why they make the decision that they've made about the language, etc. So it's really a language starting for engineering, for high performance from the beginning. So I think it's a good point. We have different applications, for example, potential of Julia for high energy physics. Next generation dynamic programming language, Julia. In this case, they talk about the biological science. And more recently, in 2019, with the use of GPU in Julia. So for us, it's also interesting because apart from DIVA-ND, we develop different tools. Some of them are based on GPU. It's really very excellent to have this possibility to work on GPU to develop our tools again in Julia. So how you would learn Julia and DIVA-ND? I would say the easy answer is to read the paper. So this paper by my colleague Alexander Barth is already 11 years ago that he started to write this paper. So DIVA-ND version 1.0, and dimensional variation analysis for ocean observation. So you need to know that at the beginning, DIVA-ND was written in MATLAB, and it was slow. It was too slow for our application, and that's why we switched from MATLAB to Julia. And we have also a set of Jupyter notebooks. So the notebooks, there are computing environments where you can use different cells. So in the Jupyter notebooks, you have cells with computation, cells with comments, etc. And what we've done, we've designed a set of Jupyter notebooks, which is accessible at this address, so GitHub, Liège, DIVA workshops. And this notebooks, the objective is that people, they download it and they can use it to learn first, learn a bit of Julia, so basics about Julia, the functions, how to create a module, etc. And then increasingly, with an increasing complexity, they can run DIVA-ND example, so interpolate basic data and then build more complex interpolation using using their own data. That's what we really want to teach when we have the DIVA-ND training course. In fact, this set of Jupyter notebooks, we're trying to publish it in the Journal of a Person's Education, so a journal where we can submit training material, and maybe it's something relevant in the frame of this project, because maybe there will be other training, etc. So this journal is, of course, open. You submit the paper, in fact, by GitHub directly. It's not a typical journal. We have how it's called, the manager for the publication. So it's quite agile. You can just submit through an issue in GitHub your paper in Markdown format, and it's formatted automatically. You get the PDF, and then all the review of the paper is done also by GitHub. So I think it's very transparent, very open, and it makes sense in the days that we're living. So now, what would be the good reasons to use Julia? I repeat myself, but it's really relevant to not forget that. So it's very, very fast, math-friendly syntax, very obvious in our case where we are dealing with high-level mathematics. It's easy to install. I put in parentheses now because it was maybe not so easy to install in the past, but now it's very something that you can install any type of machine, Windows, Linux, etc. It's easy. Even in our supercomputers here in Liège, you can do it. And the ecosystem package is really growing. So we have always more people interested in the code and in the language, and contributing very interesting modules that we are using. For example, the NetCDF reading module developed here also in Liège. But you have all these GPU-related packages. So I think, yeah, good reason to use it. And now we will talk about some applications with DIVA-ND. So the applications, there are many of them. I just wanted to give you a small review of what we are presently doing with it. But the idea is that I don't show, okay, I show a few examples of DIVA, and then you think, okay, maybe I should use it as well. I have good ideas, good data set that I could use. So in the Immonet chemistry project, we collect many data which are related to eutrophications. By eutrophication, we mean phosphate, silicate, chlorophyll, oxygen, etc. And we're asked to create a product, or gridded field of these variables. So in this case, you see the water body phosphate at 20-meter depth in May. So what we do, we create this, what we call the climatology. So it's a set of gridded fields for different depths, different time periods, in this case, a monthly time period. And we used all the observation collected in the European seas to build this climatology that we later published on a central portal, and everybody can download and using them. So what we can see here is that phosphate concentration basically is higher in the north, close to Greenland, to Iceland, etc. But there is some explanation of that, but I won't enter into details here. But that's the type of product we create. This one is interesting because, in fact, it's not something very related to our typical work. The colleagues, they've worked with physicists in the institute here. They work on astrophysics, and we have worked here on the flux duration distribution of the X-ray flare. So I cannot even explain you what it is in detail because I have no idea. But what I know is that they've used these data, so data not on Earth, but from different detectors, etc. Flux duration. So the name of the paper is this: continuation of the X-ray monitoring of SGR star. So they could use DIVA-ND, so the same code as we are using with the oceanography, to perform the gridding of a totally different type of observations. And they could do that because, again, they have coordinates, even if it's not longitude, latitude, they have coordinates to perform this. So they could apply the algorithm without any issue. Some colleagues in the Mediterranean Sea are working on climate change, and in this case, it's specific to the Mediterranean Sea climatic indices. So the goal was to use all the available data, temperature, especially, and salinity, to build kind of an atlas or collections of grid fields using DIVA, and to assess if there is a change, a long-term change in the Mediterranean Sea, and of course related to external factors. So, for example, it can be that wind has changed in the region, that there was a change in the circulations. So that's always what we want to do. We get the data. From the data, we create a gridded field, and from this field, you try to get the physical insights of what's happening in the sea. So this is another example. Again, in the Med Seas, it's quite popular area, as you've seen in our case in the oceanography, and many people are working in the Med Sea. So here we have a nutrient climatology that built using dissolved inorganic nutrients from the period 1981 to 2017. And what they wanted to show here is, again, the change in the different structure of nutrients in this area using DIVA. We've talked about the regional products, but we have also global products. When it says regional, it means we're working on a small part of the ocean or the sea, Mediterranean Sea, North Sea, Black Sea. It's where we used to work, but some colleagues in Italy also developed new global ocean climatology. And the idea, again, is always the same. They try to combine many sources of observations from different projects. They have to remove the duplicates and then apply the DIVA-ND methodology to create these gridded fields, the associated error fields, and they do that for different different time period, different depths, and different variables. So it means that you have to repeat the observation. In this case, the grid is quite big because you have to work on the global ocean. And with a very fine resolution, it means that you have a very, very fine grid. So it's very computer intensive, and it's not easy or even not possible to do it with other techniques that DIVA-ND. So what other groups do is that they divide the ocean in different subregions. They apply the technique, and then they try to reconstruct the full ocean, combining the different regions. But that's not so easy to do. And also another example is a heat map, so let's say a density map based on the observation of tropical cyclones. So we took all the trajectories and the observation of tropical cyclones on Earth, and we used the DIVA-ND not to interpolate them, but to create a heat map. So showing the brightest region is where we have the highest density of cyclones in the ocean. So now I would go back to, if you remember, the four good reasons not to work with DIVA. I would go now the good reason you would like to learn Julia and DIVA-ND, because I think we've shown enough arguments in favor of it. So let's recap that. So the DIVA algorithm, we've said it's complex, but it's complex because it can address the complexity of gridding, complexity due to heterogeneity of data, the complexity of the Earth, because you have to take into account the boundaries, the coastline, etc. So that's why we have a complex algorithm, because we are dealing with complex data, so it cannot be simple. The code is open source, and in addition, we provide Jupyter notebooks for the training. So we have the code that you might not need to understand perfectly, because it's at the end you need to be able to apply it. And that's why we provide, in addition to the code, a set of Jupyter notebooks to show you how you would use the code to create your own products. DIVA-ND can be extended to any types of georeferenced data. It can be we would really be happy to help you to use it with different types of data. In fact, I've not shown all the application, but we could also have worked on temperature measured on land, can work on any types of measurement. That's really what makes the thing exciting, because always the ocean is something that we manage now, but I think we can get new challenges working with different types of data. And Julia is fast, and in addition, it's very mature now. So it's not the language it was 10 years ago. It's good or excellent documentation. It's fast, easy to install. So I really recommend, and even for students, I think it's the future maybe to start with this type of language. So how you would learn DIVA-ND? We have online and on-site. So thanks to Benyat for the preparation of this flyer. So you have the date here. So today with the online webinar, and we have the on-site training late January. Also, you need to know that we always open to collaboration. So it means sometimes people, they contact us by email, say, look, I'd like to implement DIVA-ND on my data set. They send us subset, so we can see what's inside the data set, how to read, etc., and help them prepare the products and sometimes publish something. Also, we are quite open to have visiting scientists here in the university, so we used to that. So in case, hopefully you can come to a training, but otherwise it's always possible to organize something here in Liège. What we would do in the training session, that's the proposed agenda, it's already the same. So the first session, I call it the session 0, it's about installation, because we've noticed in the past that the problems, they arise not using the code, but installing. Even if the installation is always better, every machine is different, and people always come with sometimes old computer with different installations. So sometimes it might be the easiest part, but it might be the hardest part of it. We would install Julia, DIVA-ND, and the Jupyter notebooks with the training material. So this could be done remotely. Maybe we should organize more than one session about that, but that's the idea, that if you come to Liège, your computer is already fine to continue. The session number 1 will be an introduction. We want to talk about the Julia types, because you need to know a bit of Julia, not to be fluent in coding in Julia, but at least to understand the basics. So the types, the functions, how do you install the packages, create simple plots and reading, I would say NetCDF in our case, but can be any format. So that's really the basics. Then we have the part which is called preprocessing. So it's preparation of the input. You read your own observations, meaning that you probably need to create new functions for reading if they don't exist. Create a bathymetry to define the Lancy mask, to create the time periods where we want to perform the interpolation. Session 3 is the most important. It's where you run the analysis. You will create data products, what we call in our case data products, that are read field with sample data set that we provide, but also especially with your data set. And we have a final session, I call it the advanced topics. It contains complex types of analysis, because I've really simplified the reality of what is in DIVA-ND, but you can add some constraints. For example, in the ocean, we have currents, and we can take these currents into account during the interpolation. We can use it to perform an advention constraint, so an additional constraint into the cost function, so we can really take into account many processes or in the ocean or the atmosphere, if we know more about the physics of what is happening. So that was all. I think it was maybe fast, but at least we have some time for the discussion. So I have here my email address, the website of our group, and probably the most important is the GitHub webpage, because it's where all our codes, not only DIVA-ND, are available. So thank you for your time.
Thank you very much, Char. Um, Thank you very much for a presentation so clear in the DIVA-ND. I think it was very easy to follow in the audience as well, with people like me who were not aware of the tool. So thanks once again. I will stop the record now and we can go to the questions. Thanks also to the participants who've been attending. Let's move forward with the questions.